Okay, so this is a video to explain how to use the input files. The best thing to do is to find a file. It'll have an INP ending. If you're in Windows, it'll just look like an INP file. If you're working in Linux or Unix, then it'll have a .inp. This you can open with a text editor. I use Emacs, but it's possible to use Word, it's possible to use Notepad, whatever works. It's just a text file. The important thing in the input file are equal signs. If there's an equal sign, it's expecting something. So here we've got geometry, and there's a flag, which is equal to 1 here. If it was equal to 2, it would be a slabbed shape. We're never going to use that in my system, so that doesn't need to change. Then we're on to physical parameters. So this is where you can put in whether you have a central source. If you don't have a central source, you can switch it off and just have external, which means you have heating from the outside but not from the inside. If you have the central source switched on and the external switched off, so that's a 1 and a 0, then you have a central star but no external heating. And this is going to be the normal mode of operation for modeling AGB stars. The next item to put in it's called the central source radiation. Basically, this is your central star in the middle of your dust shell. You can put in the spectrum in different ways. We usually do it by putting in a black body. So this is spectrum equals 1, means that it's going to look for information about a black body. It's also possible to put in other shapes, and it's also possible to read in a file. So if you have a spectrum of a star you want to use, you can do that. Then how many black bodies? So you could have a system where you have a binary star with the shell of dust around it, in which case you might want to have 2 black bodies. In this case, we're just going to assume 1. This object I'm modeling is a post-AGB star. It's already getting hot. For AGB stars, we expect temperatures between about 2500 and 3500 Kelvin. As they get older and they turn into post-AGB stars, they get hotter, and so this model that is in here is for one of these hotter stars. The next thing is the temperature of the dust. So if the dust is forming at the highest temperature it can be, that depends on the density in the gas shell. And so the inner dust temperature, this is basically where the dust first forms, could be as high as 2000 Kelvin if you can form dust at that temperature, or it could be really low. In this case, it's not forming any dust anymore. The dust is drifting away, so it's getting cooler, and that's why it's so low. Temperatures above about 2000 Kelvin are unlikely. The next thing that you can put in is the dust properties. In this case, you can put in something that's embedded. So this is different types of silicate. Silicate OW and silicate OC come from a paper by Ossenkopf et al. From 1992. Silicate DL is drain and lee silicate. These are all things that astronomers commonly use to model silicate. This is graphite, this is amorphous carbon, and this is silicon carbide. And you can choose how much. And you can see in here I'm not choosing any of those. So here where it says optical properties index, if this is 1, I can only choose from this selection here, and I put in the proportions in the numbers here. If I put in 2, I can add other things. So here I'm putting in how many other things do I want. In this case it's just 1, and then underneath I list where the files are for it to read the optical properties of those dust grains. So you have to have files that have the complex refractive index. And then you say how much you want. So in this case, this is the only component, so it adds up to 1. The next property is the grain size distribution. We won't talk about that yet. We'll come back to that next time. But the size distribution default is when it's equal 1 is what's known as the MRN distribution, and that's adequate for starters. The next thing you can do is to put in the density type. So in this case, I'm actually reading in a file. This is a file that has how the density changes with distance from the star. It's also possible to put in the density type in terms of a power law. How does the density decrease as you go away from the star? 1 over r squared would be the standard. It's also possible to change the thickness of the shell. So you could say, oh, it's a very thin shell or a very geometrically thick shell. Finally, the last thing is to set the optical depth. This is basically a measure of how dense the shell is, kind of. You can do this in various ways. This one's only giving you 1. It's got a very high optical depth in the visible. So this first flag means that it's the type of grid that you want. So how many optical depths you're going to do and how you want them spaced. If it's linear, then this is 1. If it's a 2, then it's a log scale grid. And I'll put one in here so that you can see what that looks like. We set the wavelength at which we're setting the optical depth, and then I'm going to make this go from 1 to 100 in 3 models. And what that means is, since we've selected a log grid and we have 3 models, it will do a model with a tau of 1, a tau of 10, and a tau of 100. If I was to change this to a 4 and put in a 0 here, it would be 1, 10, 100, and 1000. It works out how to evenly space them in a log grid, depending on how many models you put in. You can change what wavelength you want to use for your optical depth. You can change the optical depth you want to do, and how the grid distributes itself. Those are all the things that you can play with. You should only ever play with one parameter at once. So if you want to figure out what the effect of the star temperature is, just play with that. And to figure out what the effect of the dust temperature is, just play with that. The next thing to do is to define what outputs you want. So here, basically what this does is, if you want to get out a spectrum, then you would have flag 1 or 2. 1 basically puts all the spectra in one file. Flag 2 puts them in separate files. And so depending on what you're doing, that may or may not be useful. I'm not making any images or visibility functions, but I am getting out radial profiles. So what this does is it produces a file for each model that will end in S00, so 001, I001, V001 will be the first model. S002, I002, V002, and so on will be the second model. And depending on what you actually want to look at, there's all sorts of things that we can put in to get the optimal data out. If you're looking at spectra, you don't need the images, but if you want to get the distribution of materials, then you'll need to image at different wavelengths and see what it looks like at different wavelengths. And then you just need to save your file, and then it's ready to go. When you're ready to go, if you're working on a Windows machine, then what you're actually going to do is you're going to open a command prompt, assuming you've already installed Dusty. You open a command prompt and you will go to wherever your program, your compiled program is. So you should have a version of Dusty which will be called dusty.f, and then you'll compile it and it will make a version that is executable. And then when you're ready to execute it, you just have to double click on the executable file. So here it's called an application. So when you're ready, you can just double click on that. Oh, I missed a step. Sorry. The next thing you have to do is to go to the dusty.inp file. In the dusty.inp file, you list what files you want to run. So it's basically the path name to where they are, and then what's the name of the file, but without the .inp. And then once this is ready, then you can double click on the application button and it will run those, and it will pop up a command prompt that will show you what's going on. When that disappears, your models are run and you can go and look at them. There'll be another video to explain what the outputs are.